Welcome back, everyone. A very exciting Wednesday evening. I hope you're all having a good week, and welcome to another York Observatory TeleTube. Tonight we have something very, very special planned. In fact, we are going to take a little bit of a detour here at the beginning of our broadcast. And before we discuss planetary weather, we have a special treat. We have managed to hook up York Observatory's own 1-meter telescope at the Allen I. Carswell Observatory. So if you will all just bear with me here for a moment, a small screen transition may be in order. All right, everyone, welcome to the 1-meter telescope running at York Observatory right now. This is a very exciting time. This is actually the first time that we have been able to get the observatory fully remotely operational. As you can see, we have the 1-meter telescope pointed at the moon currently, and we are on the sky. It is a little bit bright, of course, but we are pointed at the moon. We have with us tonight several people who will be presenting our main show. I'd just like to give a little introduction to our hosts this evening. Palvisha, Jean-Luigi, Sana, Noah, and a little extra shout out to Obata, who helped work on some of the slides, and Dr. Paul Delaney, who is at the 1-meter telescope right now, operating all of this remotely. Some of our presenters tonight have actually used the 1-meter in person. Um, uh, I guess I'll go ahead and give a little bit of an open floor here. Um, let's all just, what are our favorite 1-meter facts or 1-meter memories? Now that we've gotten it up and working again, Sana, do you want to talk a little bit about your Messier Marathon?
Sure. So this was actually, I believe, was the last time that the 1-meter telescope was used before quarantine started and we had to leave campus. Another observatory member and myself, Gagan, we both went up to the telescope and stayed there all night and tried to image every single object in the Messier catalog. So the Messier catalog, for those of you who don't know, is this catalog that astronomers use. It has a bunch of bright objects. I believe it's about 110 in total. And the Messier catalog was put together by astronomer Charles Messier, hence the name Messier catalog, who was a comet observer. And when he was observing the night sky and looking for comets, he kept running into these little fuzzy things that kind of looked like comets, but then he discovered that they weren't comets. So what he ended up doing was compiling a list of these objects that might look like comets but aren't. So don't look at these because I don't care about them. And he published that list so that other people who were looking at comets knew not to look at those objects. And over time, it brought up to 110 objects, with some other astronomers contributing some objects to this. Well, it turns out that in the process of doing this, he outlined 110 of the brightest and best objects that you can look at in the night sky. So now it's a catalog that amateur astronomers and even some professional astronomers will use as a guide when they're observing. And there's, I believe it's a couple of weeks to a month during the year where if you stay up all night and you have a good telescope that's great at pointing like the 1-meter is, or you know the sky very well and you can move the telescope around yourself without the aid of technology, where you can look at every single one of the objects in the Messier catalog in one night. So that's what Gagan and I did. We got about 80-ish of the objects. We imaged them with the CCD camera, and we got color images on some of them, and some of them were just single shots in only the red filter, so we wouldn't be getting color images out of those. But then we have a nice catalog of what many, many objects in the Messier catalog look like through the 1-meter telescope. So we can also use that as a guide of when we're thinking about, oh, what would we like to image next, we can use that to kind of pick.
Excellent. So tonight you'll notice, for the keen-eyed amongst you, that the telescope is in fact pointed at the moon. So we're not going to be able to observe anything as esoteric as the Messier objects right now. It is in fact still sunlight. For those of you watching the live stream, you will have noticed the sun has not set. We are able to observe the moon because it is so bright, and of course because we have the 1 meter telescope. So we'll show you a couple images of the moon through the 1 meter shortly, but since we have the live connection up, I'd just like to go ahead and give a shout out. This is what the telescope is doing right now. You can see that there's a couple different interfaces open. The plane wave interface is actually how we're controlling the telescope. You see that there's a star map of what's up in the sky right now, showing here with the sky viewer. That is showing you what you could try to go see. The moon is down in the corner with the reticule focused on it, and that's because we have moved the telescope over to the moon to take those images. Now, because they're going to the CCD, they do have to get processed by the CCD before we can view them. So I'll show you on another screen. And you will see that in this area, it's showing you everything that's up in our part of the sky, so the Toronto skies right now. So over on the other side of the sky, you can go to the west and see the sun is still up. So this little yellow blob here, that is showing us that we still have a reasonable amount of sunlight. So we need to wait until the sun goes down to view our dimmer objects like the Messier objects mentioned by Sana. If you have very good eyesight, you might have spotted on the map there are a few M's with some numbers. Those usually refer to Messier numbers, and those are very, very handy for tracking. So this plane wave interface is sort of came with the telescope. It is a plane wave telescope that we got almost a year ago. So we're very close to celebrating our 1 year anniversary. Stay tuned on this channel. In a couple weeks, we will have a bit of a party. Announcements coming shortly. But the 1 meter plane wave telescope is the largest on-campus observatory in Canada. And because it has such a large primary mirror, we are able to collect light much more efficiently and create some really, really beautiful imaging currently, as well as hopefully spectroscopy once the spectrograph gets mounted. So this grid that you see here on the image, that grid is showing where things are in the sky. So just like we have longitude and latitude here on Earth, we have coordinates in the sky, which are usually referred to as right ascension and declination, or altitude and azimuth. Our telescope uses altitude and azimuth, which is just another way of saying the same thing, but it is basically allowing you to get the coordinate number of how far up the grid I have to go and how far over on the grid I have to go before I land on my correct object, and that determines the angle of the telescope pointing inside of the dome. So the dome is currently open, and you can see that the joystick controls are also open and have been in use to tweak and focus telescope. And we'll just get a live update from Paul at the telescope right now to see where the how many images have been taken of the moon. All right. And we should be able to show you a couple of those windows. Of course, we are using all of our digital connections at the moment, sending messages to Dr. Paul Delaney over at the telescope and broadcasting this to you live from the telescope over Zoom through YouTube on our channel. So hopefully this is one of many to come. You can see in the background, um, Paul is moving around a little bit, trying to show us a couple more aspects of the observing tonight. And once he's done, I will pull up some images. Let's see if I can get the camera to show up. Here we go. Perfect. I am going to change the window here. There we go. This is the moon. Everyone, welcome to live viewing remotely. I realize the aspect ratio is a bit odd, but you are right now currently viewing the moon through the 1 meter telescope. At York Observatory, Alan I. Carswell Observatory on campus. So we're very excited. This is the first time we've been able to get it all working, and I hope that you all are having as much fun as we are. Would anyone from the crew like to shout out a favorite moon feature here?
I think I'll go. I think maybe not necessarily right now, but I think a nice view from our telescope when we look at the moon is like the details of the craters. I think it's so well refined and with such high resolution. I just love to look at the moon at any time with our 1 meter telescope.
Excellent. Noah, do you have a favorite moon feature?
Honestly, I have to agree with John Luigi. The amount of clarity and detail that you get in these images from the 1 meter are truly astounding, and I honestly can't get enough of them.
Everyone can see right now, Paul is adjusting the light levels for us. This has to do with image processing. So as the images come in, they are sent to the CCD cameras. You can see the darkness is being adjusted so that we can make out Mara as well as the craters and the different features on the moon. You can see that even though the sun is up, we are able to get a lot of detail out, especially by moving these sliders around and processing the images. This is part of something called astrophotography, which our colleague member Sana has glossed over briefly, but is a bit of an expert at. So she has a whole presentation on that, and you can see her eye poster from the recent Casca if you want to know more. This is a bit of an art form, but if I was to use this for a scientific purpose, one thing that's often done with the moon as well as other bodies in our solar system, everything from asteroids to other planets, is to look at the cratering behavior to determine the age of the surface that you have. Also analyzing the different types of craters, the layers of craters, you can see that there are dark areas on the moon. This is because the moon has actually resurfaced. It's had some volcanic activity in the past. Those Mara are not oceans. Their name comes from ocean, the word for ocean, sorry. But it is actually old volcanic activity. So if you realize that the younger surfaces are the ones with fewer craters, something must have happened in the formation of our solar system to make more craters happen earlier. And that actually goes into, how the solar system was formed, and there used to be a lot of collisions. And now there aren't so many, which we're very happy about because we have to live on a planet in our solar system. But this allows us to trace back, the age of features in the solar system, the age of the solar system, the behavior of the solar system, all kinds of interesting things. And one of the really cool things about the moon is that despite the fact that it's so sort of dry and lacking activity now, we can see what its history was by examining the features that are there now. And as some of you may have read, there are even signs of small amounts of water on the moon. So a very, very interesting place. All right, looks amazing. We could obviously stay here all night, but we do have a regular show to move to. I will just go ahead and ask any of our crew last moon thoughts before we move on to our regular broadcast. Everyone is speechless.
The moon, if I could just mention, is one of those objects it looks just as amazing through the eyepiece as it will through the camera. So if anyone has seen astronomical images and then looked through the eyepiece, you notice that the images always have so much more detail than you would see. But that's not true with the moon. It looks as good as it does on the screen when you're looking through the eyepiece. And it's always so much fun, especially with the 1 meter, to be able to take that little joystick controller that is an actual game controller and drive around the moon at a high magnification to check out these little details. And it's definitely one of the best things that you could observe, especially with the telescope like the 1 meter.
Exactly, and it is a wonderful object to go out and view at night. It just you know, it never gets old seeing features on the moon. And you know, if you do get a chance to go out and look up, that would be highly, of course, highly recommended astronomy. Alrighty, so I'm just going to give a last little recap and shout out. We have gotten this working, so look forward to more live space images. This is the moon in real time through our CCD, unprocessed images. I'm just going to show you one of our processed images here very quickly, and then we will move on to our regular show. So again, excuse the screen swaps here. Normally we don't do this, but we had an unusual chance to show you live images, and we wanted to take use of that. So here you can see one of our processed images. There was a little bit talk of filters earlier, and you know, for the moon, we usually use something called a neutral density filter, which is different from the colorized filters you heard about in this discussion of Messier objects, because the moon is very, very bright. So we actually have to worry about it saturating or overexposing on our CCD. So we need to block some of the light in order to be able to image it. Messier objects are not that bright, so we go ahead and get all of the light and separate it into filters to characterize it. Okay, so this is one of our moon objects. You can see the cratering in a little bit more detail here, as well as Mara and other features. And I'm just going to show you a couple more beautiful images as we clip through here, because this is the moon through the 1 meter telescope. And we have a bunch of these images up on our website. More are coming. But you can see that you can really do a lot with combining different image types. And I'll just end here with this image of the Terminator line, which is one of the interesting things to look at if you have binoculars or even just really good eyesight, I suppose. Binoculars or a small telescope, you can see the edge where the shadow of the moon really enhances the cratering. And that's called the Terminator line. Very, very fun stuff. Okay, this has been a wonderful side, but we do have to go on with our show. So we have a fabulous, fabulous show for you tonight. Let me just go ahead and give you one more slightly awkward transit screen. And again, apologies for the rough nature of the transfer around on the video. Okay, now we are back. So usually our videos are slightly more seamless because we have a little bit of extra time to prepare. Welcome again back to our regular program. The 1 meter telescope, as you have seen, is live and taking images of the moon right now. Now we have a fabulous broadcast for you tonight about planetary weather. So a bunch of different planets and planetary weather in general. So you might have heard that the moon does not really have much of an atmosphere, doesn't really have much weather to speak of. But some of our staff and students have, well, our students and volunteers have come up with a great discussion on planetary weather, really wrapping about what would we be doing with it and how does it all fit together. So I'll just go ahead and welcome Again, Palvisha, Jean-Luigi, Sana, and Noah, who are here tonight to present to you planetary weather. This is broadcasting live from the Alan I. Carswell Observatory, truly live tonight with the 1 meter telescope located at York University in Toronto, Ontario, Canada. Just as a reminder, we do broadcast every Wednesday night at 7:30 p.m. local Toronto time here on York U Observatory YouTube Live. If you have questions, please feel free to email us at observe@yorku.ca or ask us in chat at any time during this live broadcast. You can also follow us on Twitter and Instagram at York Observatory. So please feel free to tune in, and we'll go ahead and get tonight's show started. Okay, take it away, crew.
Thank you, Dr. Hyde. Good evening, everyone. I'm Palvisha, and I'm here today with Sana, Jean-Luigi, Noah, and Abada from York University's Alan I. Carswell Observatory. We'll be talking all about space weather, starting with our own planet, and then going into weather on other celestial bodies in our solar system. We hope you enjoy the presentation. Space weather is an incredibly interesting topic. But before we can jump into what it's all about, it's crucial to understand weather and how it works within our own planet. So, I'm going to start off talking a bit about Earth's weather and our atmospheric system. First off is the atmospheric composition. So, the atmosphere is composed of a few different gases. It's composed of 78% nitrogen, 21% oxygen, 0.9% argon, and less than 0.1% of the composition of the atmosphere is trace gases such as carbon dioxide, nitrous oxides, ozone, and water vapor. Water vapor is really interesting in that depending on what sort of climate you're in, it could either be a large part of the 0.1% trace gases or a very little part. So if you're in a humid climate, it would constitute a larger fraction, and if you're in a dry climate, it would constitute a lower fraction. Earth's atmosphere is further divided into different layers. From the lowest in elevation to highest, the layers are the troposphere, stratosphere, mesosphere, thermosphere, ionosphere, and exosphere. The thermosphere, ionosphere, exosphere, and mesosphere are kind of interesting in that the ionosphere actually overlaps several of these layers, but I'll get into that in a bit. So the troposphere is the layer that starts at the surface of the planet. It's what we have all around us. It extends from the surface of the planet to about 8 to 14.5 kilometers high. It's the densest layer, and it's where all of our weather occurs. Right above the troposphere is the stratosphere. It extends to an elevation of 50 kilometers high and contains the ozone layer, which absorbs harmful UV rays from the sun, protecting life on Earth. Right after the stratosphere is the mesosphere. It's the layer in which meteors burn, and it extends to an elevation of about 85 kilometers high. Right after the mesosphere is the thermosphere, and this extends to an elevation of around 600 kilometers. It's the layer in which the Aurora Borealis occur. Within the thermosphere and beyond is where you can find satellites. And next up, you have the ionosphere. So the ionosphere actually starts at 48 kilometers above the surface of the planet and extends to 965 kilometers above the surface of the planet. So just at the cusp of space. It overlaps the thermosphere, mesosphere, and the exosphere, which I'm going to talk about next. The exosphere is the outermost layer of the atmosphere. It extends to an elevation of around 10,000 kilometers, after which is the emptiness of space. This is where air molecules can escape the hold of Earth's gravitational force. As you go higher into the atmosphere, the layers decrease in density, and you would assume that means that they decrease in temperature as well. This is only partially true. Some of the layers do follow this logic, but some of them don't, and I'll talk a bit about why. So as you go higher in the troposphere, the temperature does decrease as expected, but when you go into the stratosphere, it actually increases. And this is because of the presence of the ozone layer, which absorbs large amounts of radiation. The mesosphere, right after the stratosphere, also follows the expected trend with a decrease in temperature, but the thermosphere and beyond actually experience an increase in temperature. And this is due to the fact that there are ionized atoms from the ionosphere, and very large amounts of solar radiation are incident on these layers. So now that we know a bit about the layers of the atmosphere, let's focus on the troposphere, the layer in which all of our weather takes place. The temperature in the troposphere can range from 17 degrees Celsius to around -52 degrees Celsius as you climb higher in the troposphere. Keep in mind, this is not the same as Earth's surface temperature. I'll talk a bit more about this later, but Earth's surface temperature, which does not change with elevation, but rather depends on a location's longitude and latitude, ranges from -89 degrees Celsius in Vostok Station, Antarctica, to about +70 degrees Celsius in the Lut Desert, Iran. The longitude and latitude of these locations contributes to their temperature, as their location on Earth, or how high or low they are relative to the equator, determines how much sunlight they can receive throughout the year. There are several different types of weather systems that can occur as a result, and I'm going to focus on just two of them, but you can have everything from thunderstorms, supercell thunderstorms, hurricanes, blizzards, tornadoes, and more. So I'm going to focus on tornadoes and hurricanes specifically, as they provide a good base to move on to discussions about space weather. So what are tornadoes and hurricanes, and how do they form? Well, starting with a tornado is a rapidly forming column of wind that extends out from the storm clouds to the ground. They form from supercell thunderstorms specifically, which are a special type of thunderstorm that have a rotating vortex. They're produced when hot and cold air masses meet, and the warm air strengthens the rotating vortex, creating a funnel cloud. If the funnel cloud touches the ground, it becomes a tornado. Tornadoes have some of the strongest winds on Earth. A typical tornado can have winds of 65 to 165 miles per hour. The strongest tornadoes can have winds of over 200 miles per hour. Now you have hurricanes. So hurricanes are also called typhoons in the Northwest Pacific and cyclones in the south. They're large, rapidly rotating storm systems with a low pressure area at the center, which is the eye of the storm. They form over hot water or warm water, which is rich with moisture. And like with a tornado, they form due to the interaction of cold and hot air masses. However, they're much larger in area. A hurricane forms when a low pressure system moves over the tropical ocean or warm water, absorbing heat and moisture. The longer a hurricane spends over water, the more moisture it obtains, and the stronger it gets. The rotation direction of a hurricane depends on whether it's located in the northern or southern hemisphere, due to what's called the Coriolis effect. The Coriolis effect causes air masses in the northern hemisphere to rotate clockwise and counterclockwise in the south, and it's just the result of Earth's rotation. As terrifying as tornadoes and hurricanes may be, unfortunately, they're due to get worse due to rapid changes in Earth's climate as a result of the greenhouse effect. I'm sure you've all heard of the greenhouse effect, but just as a refresher, the greenhouse effect is essentially a mechanism allowing the absorption of heat on Earth. Due to the gases in our atmosphere, specifically the troposphere and stratosphere, the heat and radiation from the sun is not completely reflected back out in space. Some is absorbed by the gases in these two layers and contributes to Earth's surface and oceanic temperatures. The heat absorbed due to the greenhouse effect not only drives our weather and storm systems, but is also the reason Earth can host life. If it were not for the greenhouse effect, the average surface temperature on Earth would be about -18 degrees Celsius instead of the current 15 degrees Celsius. Unfortunately, due to an increase in carbon dioxide and other greenhouse gas emissions, more heat is being trapped by the atmosphere. This not only raises the ocean and surface temperatures, but also makes life harder for aquatic life, increases instances of droughts, and makes storms such as tornadoes and hurricanes much more intense and frequent. I want to end off this introduction to weather and weather on Earth on a lighter note and talk a bit about the Aurora Borealis. As you'll find out in a bit, Earth isn't the only place where you can experience these magnificent light shows. The Aurora Borealis, also called the Northern Lights, commonly appear in a pale green or pink color, although shades of red, blue, and violet have also been reported. The auroras form when gaseous particles of Earth's upper atmosphere collide with the ionized particles from the sun. The ionized particles from the sun reach Earth through what are called solar winds. The gas particles excite, and depending on which gas particle it is, produce light in different colors. For example, the common pale yellow-greenish color of the Aurora Borealis results from the collision of oxygen molecules with the charged particles from the sun. These are produced at a height of about 60 miles above the Earth's surface. Red Aurora Borealis, which are incredibly rare, are formed by oxygen at a height of about 600 miles above the Earth's surface. Purplish red or blue auroras are formed by nitrogen interacting with the magnetic fields. And so as the magnetic fields or the magnetic poles start to shift, you might have a harder time seeing the aurora here in Canada.
Before we discuss the rest of our solar system planets and their composition and weather, let's have a look at some other celestial objects that usually you won't think right away they could have some similarities with our dear planet and possibly be or were host of life. First up, it's Europa, which is one of Juniper's moon, which is slightly smaller than our moon. At just over 3,100 kilometers in diameter, it is the sixth largest moon in the solar system. Its bulk density suggests that it's similar in composition to the terrestrial planets, being primarily composed of silicate rock. From the Galileo orbiter, Europa showed an induced magnetic field through interaction with Jupiter's, which suggests that the presence of a subsurface conductive layer. Such a layer is estimated to be of salty liquid water of about 100 kilometers thick. Thanks to the Goddard high-resolution spectrograph of the Hubble Space Telescope, Europa revealed to have a thin atmosphere composed mainly of oxygen and water vapor. Unfortunately, this oxygen presence is not of biological origin, like on Earth. Instead, it is due to radiolysis, a dissociation of molecules through radiation. The existence of water underneath Europa is still ethereal, though. Images taken from Voyager and Galileo showed some chaos terrain, a common region on the planet where scientists think it is the sub-ocean melting through the icy crust surface. Another theory is the thin ice model, which suggested that Europa's ice shell may be only a few kilometers thick. An interesting fact about the Galilean moon is that its radiation level on its surface is estimated to be about 5,400 MSB per day. Such amount will cause severe illness or death in human beings exposed for just one day. Unfortunately, we might have to move along and uncover a new place for colonization. Titan, which is the largest moon of Saturn and the second largest natural satellite in the solar system, it is the only moon known to have a dense atmosphere and the only known body in space other than Earth where clear evidence of stable bodies of surface liquid has been found. Titan is the only known moon with a significant atmosphere, and its atmosphere is the only nitrogen-rich dense atmosphere in the solar system. Voyager mission showed how actually the moon is denser than Earth with a surface pressure of 1.5 atm. The discovery of methane on its polar caps led the theory of possible life on the moon, which not only are made of water, but also present on Earth. Titan is actually pretty cold, about minus 180 Celsius degrees. Hence, water ice has such low vapor pressure that little water vapor is present on the stratosphere. Because of the cold weather, opposite to Earth, greenhouse effects, consequence of methane or ethane cloud presence, like you can see in the picture, on Titan's surface prevents the planet to be far colder than already it is. Despite Titan has been around since the early formation of the solar system, an explanation to its young surface leads to a geological process that may have been reshaping the surface of the planet. Since its atmosphere is twice as thick as the Earth, only Cassini spacecraft using infrared instruments managed to map images of some portions of the moon. These images showed rough and smooth surface areas with volcanic origin, disgorging water mixed with ammonia onto the surface. It is thought that the abundance of smooth areas might have been filled by raining hydrocarbons or volcanoes. The radar altimetry on the Cassini suggested an average surface elevation no higher than 150 meters with some peaks of 500 meters. Next is Triton, which is the seventh largest moon in the solar system and is modestly larger than the dwarf planets Pluto and Eris. Due to a long history of melting, it is believed that its surface is differentiated, just like on Earth, into a solid core, a mantle, and a crust. Thanks to the water, Triton's mantle is compressed into a core of rock and metal. There is enough rock in Triton's interior for radioactive decay to maintain actually a liquid subsurface ocean to this day. Observations show Triton's atmosphere to be thin and full of annealed frozen nitrogen, with some trace of carbon monoxide and methane by the surface. Unlike other atmospheres, Triton lacks a stratosphere and instead has a thermosphere from altitudes of 8 to 950 kilometers and an exosphere above that. Due to turbulences, there is also a troposphere, which, suggested by geyser strikes, is driven by seasonal winds capable to move materials by micrometer in size. Lastly, Triton is geologically active, where its subsurface processes are similar to those that produce volcanoes and rift valleys on Earth, but with water and ammonia as opposed to liquid rock. On one of the largest cryovolcanic areas on Triton, Leviathan Patera, two enormous cryolava lakes are seen northwest of this caldera, like you can see in the picture. Because the cryolava on Triton is believed to be primarily water ice with some ammonia, these lakes will qualify as stable bodies of surface liquid water while they were molten. This is the first place such bodies have been found aside from Earth, and Triton is the only ice body known to feature cryolava lakes. But for a moment, let's step out of the solar system and have a quick look at some distinct and notable exoplanets that caught the attention of astronomers regarding their composition and similarity to Earth. Here's some candidates. The first one is Kepler 62f, which is a super-Earth exoplanet. It is orbiting within the habitable zone of the star Kepler 62, the outermost of 5 such planets discovered around this star by NASA's Kepler spacecraft. It is located about 990 light years from Earth in the constellation of the Lyra. The exoplanet was found by using the transit method and is one of the more promising candidates for potential habitability, as its parent star, it's distant from the parent star about 0.718 astronomical units from it. It's a relatively quite quiet star and has less mass than the Sun. Due to its mass of about 2.8 times the Earth, Kepler 62f is likely to be a terrestrial or an ocean-covered planet. However, key components of the exoplanet still need to be assessed to determine habitability, such as its atmosphere, if one exists, and if it lies within the outer, since it lies between the outer part of its all-stars habitable zone. Given the planet's age, its irradiance and radius, and its rocky composition, is determined that it might sustain an amount of water underneath. Although Kepler 62f may be an ocean-covered planet possessing rock and water at the surface, because it's furthest out from the star, it might lack an atmosphere. Furthermore, the low stellar activity of the orange dwarf like Kepler 62, creates a relatively benign radiation environment for planets orbiting in their habitable zone, increasing their potential habitability. And lastly, another worth mentioning is Proxima Centauri b. This planet orbits the habitable zone of a very well-known red dwarf star, Proxima Centauri, which is located approximately 4.2 years away from Earth, being the closest and maybe habitable exoplanet to us. The exoplanet orbits the star at a distance of roughly 0.05 astronomical units with an orbital period of approximately 11.2 Earth days, and was found using the radio velocity method in 2016. Without its orbital inclination known, the exact mass of Proxima Centauri b is actually unknown, as well as its radius. In fact, if the exoplanet had a rocky composition and a density equal to that to Earth, its radius might be about 1.1 Earth radius. Like many super-Earth-sized planets, Proxima Centauri b might have an icy composition like Neptune, with a thick enveloping hydrogen and helium atmosphere. The planet has about an equilibrium temperature of 234 Kelvin, which is about minus 39 Celsius degrees, somewhat colder than Earth, which is about 255 Kelvin. Because the planet is subjected to stellar wind pressure of more than 2,000 times the Earth, its atmosphere might have been blown away, leaving the undersurface as the only potentially habitable location on that planet. Also, another problem with the exoplanet is that the flares released by the host star Proxima Centauri could possibly have eroded the atmosphere of the planet by the years. Unfortunately, the missing details of an atmosphere does not allow scientists to determine Proxima Centauri be habitable as yet, but thanks to its vicinity, with the help of telescopes, it will be easier to reveal more about its composition and atmosphere.
Now let's return to our solar system and take a look at the rest of the terrestrial planets, Mercury, Venus, and Mars. These are all classified as terrestrial planets since they are all rocky planets with a solid surface. First off is Mercury, which is the closest planet to the Sun. Mercury is also the smallest planet in our solar system, even smaller than some of Jupiter and Saturn's moons. Because Mercury is so small and because it's so close to the Sun, it cannot hold on to a substantial atmosphere. However, it does have an exosphere with a pressure of 1/4 that of the Earth, so it does not experience storms or any other kind of weather that we are used to on Earth. One consequence of Mercury's thin exosphere is that it is unable to retain heat from the Sun due to lack of the greenhouse effect, meaning it experiences massive temperature extremes. On the side of Mercury that faces the Sun, it reaches temperatures of 430 degrees Celsius. However, on the side that is not facing the Sun, it has temperatures of about -170 degrees Celsius. The lowest temperatures on Mercury are cold enough for water ice to exist, and this is exactly what is found in the polar regions of Mercury, which are permanently shielded from sunlight due to its orbit. Moving out to the next planet from the Sun, Venus, we find a very different story. Unlike Mercury, Venus has an incredibly thick and dense atmosphere, composed mainly of carbon dioxide, along with nitrogen and some other trace gases such as sulfur dioxide. Its atmosphere acts as a blanket, trapping heat from the Sun and giving the planet a more or less constant surface temperature of about 470 degrees Celsius, which is hot enough to melt lead. Its thick atmosphere also makes the pressure at its surface incredibly high, with an atmospheric pressure 92 times that of the Earth. This combination of pressure and temperature makes it nearly impossible to send landers, let alone humans, to the surface of Venus. There have only been a handful of successful landers sent to Venus, with the successful ones being melted and crushed by Venus's atmosphere after enduring the long descent down to the surface. The images on the slide are of the surface of Venus and were taken by the Soviets' Venera 13 spacecraft, which survived for only 2 hours after landing. The weather on Venus is extreme. At the cloud tops, the wind reaches speeds of 306 kilometers an hour, and closer to the surface of Venus, although the winds are much milder, the thick atmosphere does create smaller currents, similar to water currents. Venus also has storms, complete with lightning driven by volcanic eruptions and sulfuric acid rain. Despite all this, Venus is sometimes referred to as Earth's sister planet, since both Venus and Earth are similar in size and composition. So why is the weather on Venus and Earth so different? This difference is due to the runaway greenhouse effect on Venus. Scientists believe that early in its history, Venus was even more Earth-like, with lower surface temperatures and even lakes of liquid water at the surface. However, Venus began to heat up, causing the water to evaporate and further heat the planet, since water vapor is a very powerful greenhouse gas. This effect was amplified when much of the carbon dioxide trapped in rocks also evaporated, creating an even bigger greenhouse effect. This continued over time and formed the Venusian atmosphere that we know today, that gives rise to the strongest greenhouse effect in the solar system, and makes the planet even hotter than Mercury, despite being much further away from the Sun. Last up from the terrestrial planets is our beloved red planet Mars. Mars is known to be one of the least hostile planets and quite possibly home to some microbial life. With a terrain very similar to some tundra environments here on Earth, sending humans to Mars has been a long-time goal of many space agencies, including NASA. But don't mistake its familiar terrain to be that too easy to live on. Mars's atmosphere on the surface is 1% the density of Earth's and is composed of almost entirely of carbon dioxide, making the pressure difference deadly and the air unbreathable. Mars also doesn't have a magnetic field, which is absolutely crucial for protecting us from other sensitive light forms from solar radiation. This is also the reason why Mars's atmosphere is much thinner. The absence of a magnetic field allows for solar winds to gradually carry away the air and decay the upper atmosphere. The red planet is also known for its harsh sandstorms that last at least a few days and can reach speeds of up to 100 kilometers an hour. If there are any fans of the Martian movie, you would know how destructive these storms are for any possible settlements. Despite all this, living on Mars is still possible with improving technologies. Mars has an average surface temperature of minus 62 degrees Celsius, which is in fact very tolerable to us sensitive humans. This is almost identical to the surface temperatures on Antarctica, where many research outposts are located. Also, due to its axial tilt, Mars has seasons, which permits a better distribution of heat and increases weather activity. The cold temperatures on Mars also allow for ice. Its polar ice caps are made of both frozen carbon dioxide and water. There is also water found beneath the surface and even water vapor in the atmosphere. From data collected by the 2008 Phoenix lander, NASA scientists have also concluded that snow is possible on Mars at higher altitudes. The current Martian rovers, probes, satellites, and the 3 upcoming missions to Mars, including NASA's Perseverance rover that is set to launch tomorrow morning at 7:50 a.m. EDT, all show very promising signs and very interesting weather patterns. Moving further out into the solar system, Noah will tell us about the gas giants.
Thanks, Anna. All right, so now that we've discussed terrestrial planets, we're going to move on to the next planets in the solar system. Gas giants, or planets composed primarily of gases, typically hydrogen and helium, the weathers of which are often extremely well known. Here, we're going to dive into some of that. So let's start with Jupiter, the largest planet and the first gas giant out from the sun. Of all the things Jupiter is known for, it's famous for its storms, particularly the Great Red Spot in the left image. This storm, similar to our own hurricanes, is over 300 years old, lasting for so long due to the lack of a solid planet to slow it down. In fact, its diameter, at the widest point, is equivalent to the distance of 3.5 Earths. Although this is the most popular storm on Jupiter, and probably in the solar system, just earlier this year, on May 31st, another convective storm near the Great Red Spot was noticed, currently known as Clyde Spot. Not only that, but at both of Jupiter's poles lie cyclones, thousands of miles in diameter, which you can see in the incredible image featured on the right. Aside from the infamous storms on Jupiter, the planet also has a thick atmosphere made of hydrogen and helium. It has 3 layers that span a whopping 71 kilometers, the outermost of ammonia, the middle of ammonium hydrosulfide crystals, and the most central one of water. Another key feature of Jupiter's weather is its clouds. Did you know that the striped appearance of Jupiter is actually due to the ammonia and water clouds, which mix with gases of sulfur and phosphorus from the planet? Due to Jupiter's fast rotation, jet streams are created, forming clear distinctions between the dark and bright clouds. The result of stripes is depicted on the image on the left. Similarly, Jupiter's winds have an immense speed, known to be between 309 and 644 kilometers per hour. And just as speed varies greatly, the temperature does too. In the clouds and atmosphere, the temperature dips to around negative 145 degrees Celsius, while in the core of the planet, the temperature can increase to nearly 24,000 degrees Celsius. Something interesting about Jupiter is its strong magnetic field, affecting what is known as the Jovian magnetosphere, spanning between 1 and 3 million kilometers towards the Sun, and 1 billion kilometers in the opposite direction, towards Saturn. This intense field causes not only high levels of radiation, but beautiful aurorae to form at the poles, as seen on the right. If you haven't noticed, pretty much everything about Jupiter is extreme, and the pressure is no exception, as Jupiter, in fact, has pressures so great that there are entire oceans of hydrogen liquid. One of the most fascinating aspects of Jupiter is that, even though it is unlikely for life to occur on Jupiter, according to the mission Juno site, and I quote, "Still, at certain altitudes in Jupiter's atmosphere, there do exist chemicals that are necessary for some sort of exotic life form. The temperatures are warm enough, and flashes of lightning could provide energy that drives the chemical reactions needed for life." End quote. These potential organisms, due to the gaseous state of the planet, are considered floaters. Next in line is Saturn, the planet known for its rings. If you can't guess based on the ice that forms these rings, this gas giant is around 1.5 billion miles from the sun, and the rings aren't the only consequence. Saturn has a temperature of negative 176 degrees Celsius. You will start to notice soon that Saturn shares many of the same qualities with Jupiter. It has a similarly thick atmosphere of mostly hydrogen and helium, though it differs with the addition of methane and water, and high winds actually cause it to have stripes as well. These winds can reach an enormous 1,800 kilometers per hour. The storms formed as a consequence, one of which is on the top of the left image, can be differentiated by their color. While larger storms appear as bright spots, smaller storms are darker. Also, just like Jupiter, the clouds, known as cloud decks, are made of ammonia, ammonium hydrosulfide, and water in the troposphere. And, if you couldn't guess, particles from their moons, plus Saturn's quickly rotating magnetic field, form aurorae too. A fascinating fact of Saturn's weather and conditions is the presence of the hexagon at the North Pole, where a six-sided jet stream forms its geometric shape. These winds of around 322 kilometers per hour surround a rotating storm. This is illustrated on the right by an image taken from the Cassini spacecraft. And finally, one of the most interesting qualities of Saturn is that it is rumored to rain diamonds. Lightning is speculated to split up methane from the atmosphere into pure carbon, or soot, which has the great potential to be compressed into another pure carbon structure, known to humanity as diamonds, from massive pressure and equally as high temperatures. The conditions that cause this are actually present on Jupiter, Uranus, and Neptune too. So for all we know, half the planets in our solar system rain some of the most sought-after stones on Earth. To finish off the planets in our solar system, we must discuss both Uranus and Neptune, commonly known as ice giants. From their crazy far distances from the sun, both have average temperatures of negative 218 degrees Celsius in hydrogen, helium, and methane atmospheres, the methane of which causes the blue that can be seen of both planets. The methane absorbs red light and expels the bluish color that reaches our eyes. What you may not know is that Uranus and Neptune both have clouds that are suspected to be made up of hydrogen sulfide. Differences, though, lie in the storms of these two planets. On Uranus, these massive events can be half the size, if not more, of the USA. Around its north pole, a storm is actually present, and has been for a long time. You can see this as the bright spot on the top of Uranus, potentially due to its rotation in a near 90-degree tilt, as you can see on the left, enabling the sun to shine on this pole for Uranus's entire summer. When the seasons change on Uranus, the atmosphere follows, and this is suspected to have caused this storm. There's also a cloud of methane near this cap, as well as near the equator of Uranus. All of this is depicted in this central image. At the same time, the farthest planet from the sun, Neptune, featured on the far right with winds reaching 1931 kilometers per hour, the fastest winds in our solar system, has a dark storm of just less than 11,000 kilometers in diameter that has just recently begun brewing. You can see this in the top of the image, slightly to the left of the center of Neptune. As is common, it is surrounded by what are known as companion clouds, the bright areas around the dark storm in the image, formed as byproducts of the storm itself. These planets and their accompanying weather are endlessly intriguing, and although I could go on forever, you've now heard the key features of the gas giants. Keep an eye out, as more information is always being discovered. Well, that's it for tonight. Thank you so much for joining us this evening. You have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Palvisha, Gianluigi, Sana, myself, Noah, and Obata from behind the scenes. Make sure to leave any comments in the comment section of the video below. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in. Clear skies and have a good night.
Thank you again, everyone, for a wonderful presentation. And just for anyone in the live stream, we will be online for about the next 10 minutes or so to answer any questions. About only 10 minutes due to the long nature of tonight's TeleTube, but please feel free to ask us anything there while we're on. Thanks.